Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today, we're exploring the massive shifts occurring in the global plastics industry, the circular economy, and the technological breakthroughs redefining how we manage materials in 2026.
And, we really have to set the table properly here. We aren't just talking about remembering to toss your water bottle in the right bin.
Right. This isn't about that little bit of guilt you feel when you get takeout.
Exactly. We are looking at a stack of research that outlines a fundamental, almost a tectonic shift in the global economy.
It really feels like a shift. For so long, I think sustainability felt like a marketing term.
Is a buzzword.
Totally. Something a company would put in its annual report to look good. But looking through these sources, the 2026 Trends to Watch report, the Pew study, the articles in Science, it feels like we've moved way past the nice-to-have phase.
We're into something much more aggressive.
Aggressive is the perfect word, and you framed the timeline so clearly. We are looking specifically at the landscape of 2026. The sources call it a renaissance for circular plastics, which sounds really positive.
It sounds lovely, doesn't it? But it's a renaissance born out of necessity. And it's being driven by some very strict, heavily enforced regulation.
Which brings us to the red tape in our title today. Usually when business people talk about red tape, it's a negative.
It's a barrier. It's bureaucracy.
But something that slows things down. But you're suggesting this red tape is actually the engine for all this innovation.
It's the constraint that forces creativity. I mean, think about it. For the last 30, maybe 40 years, plastic was cheap, it was easy, it was disposable.
Because no one was paying the real price.
No one was paying the true cost of it. The red tape coming in 2026, it fundamentally changes the math. It makes waste expensive. And you know what happens when waste becomes a major line item on a balance sheet?
Companies get very, very creative about not making it. So let's lay out the roadmap for everyone listening. We're going to start by walking through these new laws, the ones that are effectively rewriting the rules of the game for manufacturers.
Then we get into the cool stuff, the science.
The really cool science. I mean, plastic-eating enzymes? That sounds like something out of a movie.
And we'll explain why it's so different from just, burning the plastic, which is what some older tech did.
We'll also look at algae, which is a whole other world, digital watermarking, which is fascinating. And then we'll wrap up with a case study on wind turbines that, I have to say, I found honestly shocking.
The wind turbine case is a perfect example of why none of this is black and white. There are always trade-offs.
Okay, but let's start with the timeline. Why 2026? Why is that the magic number? Is it just a nice round number that forecasters picked?
No, not at all. It's a convergence point. If you look back, the real catalyst for this started years ago with China's national sword policy.
Right, I remember that. That's when China basically stopped being the world's recycling bin.
That's a great way to put it. For decades, the West, the U.S., Europe, we just shipped our trash, our low-grade plastic waste, to China. It was out of sight, out of mind.
And then China said, no more.
We're done. And it caused an absolute crisis in the global waste management system. But that crisis, that's what birthed the international treaties and the domestic regulations that are finally coming into full force in 2026.
So the playground rules are finally being enforced.
The playground rules are becoming codified federal and international laws, and the big date to circle on your calendar is August 2026.
What happens in August 2026?
That's when the European Union's Packaging and Packaging Waste Regulation, or PPWR, becomes fully enforceable.
PPWR. It sounds like another one of those acronyms you just kind of gloss over in a report.
It does, but this one is different. Looking at the details, this is nothing like the voluntary pledges we've seen from big corporations in the past.
How so? What makes it different?
It's night and day. A voluntary pledge is a company saying, we will try to use 20% less virgin plastic by 2030. It's a PR statement.
With no real teeth.
No teeth at all. The PPWR is the law saying you will use 30% recycled content in this specific type of bottle by this date, or you will be fined millions of euros. It's not a suggestion. It's an operational requirement. It even goes so far as to ban specific formats.
It bans them outright. Like what kind of formats?
Things that are deemed unnecessary or impossible to recycle effectively. So, single-use plastic packaging for fresh fruits and vegetables in supermarkets.
So no more shrink-wrap broccoli.
That's the goal. Or, those little tiny shampoo and conditioner bottles in hotels, those are on the chopping block too. The point is, if you're a brand selling into the European market, you don't get to choose anymore. The law dictates your packaging design.
Okay, let me play the skeptic for a second, though. We've seen regulations before. Companies are smart. They find loopholes, or they just absorb the fine as a cost of doing business and pass it on to us, the consumer. Won't this just make my groceries more expensive?
It's a fair question, and in the short term, yeah, possibly. There might be some price adjustments. But here is where that red tape argument gets really interesting. The forward-thinking leaders, the ones profiled in these reports, they don't see this as a tax. They see it as a moat.
A moat, like a castle moat, a defensive thing.
Exactly. Think about it. If you can master this incredibly complex regulatory environment, if you can re-engineer your supply chain to be circular, if you can secure a stable supply of the high-quality recycled material that is suddenly in massive demand, you have a huge advantage.
You're saying you can lock out the competition.
You lock out the lazy ones. The companies that are just greenwashing or the ones still trying to get by on cheap virgin plastic from overseas, they get priced out of the market. They get hit with non-compliance fines. Their products get rejected at the border.
So the regulation becomes a tool to kill off your less prepared competitors.
That's the theory. Compliance becomes a competitive advantage. And this isn't just a European phenomenon. We're seeing a globally synchronized shift towards what's called extended producer responsibility, EPR.
I see EPR everywhere in these documents. It sounds like another piece of corporate jargon. What does it actually mean for a company making, say, a laptop?
It's actually a pretty simple concept, but with really complex execution. Historically, if a company made a product, a laptop, or a soda bottle, their responsibility for it ended the moment you bought it from the store.
Right. It's mine now. If I throw it in a river, that's my problem.
It's your problem or society's problem, the taxpayer's problem to clean it up. EPR flips that script entirely. It shifts the financial and physical burden for a product's end of life back to the company that made it.
So if I'm a big electronics company or a beverage giant, I am now financially on the hook for that product forever.
You're on the hook for its collection and recycling. You have to pay into a centralized system, a producer responsibility organization that manages the recycling or proper disposal of that item when it's thrown away.
And Europe is pushing this hard.
Very hard. Their Circular Economy Act is aiming to double the EU's circular material use rate to nearly 24% by 2030. But the most disruptive application of this is in textiles.
Clothes. You mean my t-shirt?
Fast fashion. The EU's Waste Framework Directive is rolling out EPR for textiles. Just stop and think about the implications of that for a second.
That seems almost impossible to manage. I mean, you buy a cheap t-shirt for $5.
Yeah.
If the company that made it also has to pay for its eventual recycling, that entire business model just breaks, doesn't it?
That is exactly the point. The business model of selling a shirt for $5 that's designed to fall apart after 3 washes is the problem. The EPR fees are specifically designed to make that model unprofitable.
So it's an existential threat to the whole fast fashion industry.
Or a very strong correction signal from the market. And look, we're seeing this in the U.S. too, which is kind of surprising. The U.S. usually resists this sort of top-down regulation.
But it's happening at the state level.
At the state level, yeah. California is leading the way, of course.
Always. You're talking about SB 54.
Senate Bill 54, it's a monster piece of legislation. It requires a 25% reduction in plastic packaging by 2032. And that's not just a recycling target, that's an actual reduction in the amount of plastic being put on the market in the first place.
Wow, a 25% cut is huge.
It is. And then you have states like Maine and Oregon that are finalizing their fee structures right now. But the real genius of this system, the mechanism that actually drives the good behavior, and this gets back to your question about how it all works, is something called the modulated fee.
Okay, break that down for me. I'm a product designer at a big company. I'm sitting at my desk designing a new bottle for laundry detergent. How does a modulated fee change the decisions I make?
Great question. Let's walk through it. Okay, so you have 2 options on your screen. Option A is a simple, clear PET plastic bottle. It has a simple plastic cap. It's easy to recycle.
Okay.
Option B is a really cool-looking, opaque, bright red bottle. It has a shiny metal cap and a paper label that's glued on with the super strong adhesive.
The red one looks way cooler on the shelf. The marketing department is definitely going to want the red one.
Marketing always wants the red one. Now, in the old system, both bottles cost about the same to produce. But under an EPR system with modulated fees, the fee you, the producer, have to pay to the government for putting that red bottle on the market is significantly higher, maybe 10 times higher.
Why? What's the logic there?
Because you've made the recycler's job a nightmare. That red pigment contaminates the clear plastic recycling stream. It turns everything a murky gray. The metal cap is a contaminant. The glue from the label gums up the shredding machines. So the system charges you a penalty for making things difficult.
I see. So the fee isn't just a flat tax on all plastic. It's a tool for behavior modification.
It's a design tool. It monetizes bad design. If you choose the simple, clear bottle, you pay a much lower fee. So suddenly, your company's CFO is walking into the marketing meeting and saying, guys, we're going with the clear bottle because the red one completely destroys our profit margin.
That is fascinating. It forces the economic incentives to align with the recycling infrastructure.
And that's the key. We're seeing this model spread globally. Chile is a fantastic leader in Latin America. They aren't waiting for the US or Europe to figure it out. They've already got an EPR law for really tough items like batteries and electronics. It's becoming a global standard of doing business.
But even with all these laws, I have to admit, I look at the sheer scale of the mess we're in and it feels overwhelming. That Pew Charitable Trust's report, Breaking the Plastic Wave, it paints a pretty grim picture if we don't get this right.
It's a horror show if we don't act. They modeled what they call a business as usual scenario. This is what happens if we just keep consuming and producing the way we are.
Yeah.
And in that scenario, the amount of plastic pollution flowing into the ocean triples by 2040.
Cripples. We're already finding microplastics in human blood, in the Arctic ice, in the deepest parts of the ocean. Tripling that seems, apocalyptic.
It's unsustainable in the most literal sense of that word. The system simply collapses under the weight of its own waste. But the report isn't just doom and gloom. It also models a system transformation scenario.
This is the best case scenario, the optimistic view.
I'd call it the hard work scenario. It's not a fantasy. It argues that we can reduce annual plastic pollution by about 80%, maybe even up to 90% by the year 2040.
Wow.
And here's the kicker. We can do it using technologies and policies that already exist today. We don't need to invent some miracle machine. We just need the political and economic will to deploy what we already have.
But that requires a massive decoupling, right?
Decoupling utility from harm. That's the core concept, and it's one that's hard for people to get their heads around because we have this tendency to demonize the material itself. We just say, plastic is bad.
Well, when you look at pictures of the Great Pacific Garbage Patch, it's a pretty easy conclusion to jump to.
Of course. But then, walk into a hospital. IV bags, sterile tubing, syringes. That's all plastic. Look at food safety and preservation. Plastic is a miracle material. It's lightweight, it's durable, it's incredibly versatile. The problem isn't the plastic molecule itself, it's the linear journey we send it on.
The take, make, waste journey.
Exactly. We drill for oil, a finite resource. We make a plastic bag. We use it for an average of 12 minutes to carry our groceries home. And then we bury it in a landfill where it will sit for 500 years. It's an insane system.
So the goal of this system transformation is to create what the report calls a molecular economy. What does that mean?
It means we keep the carbon in play. We stop treating plastic as disposable and start treating it as a durable, valuable material that we can use over and over again.
So part of that has to be stopping the extraction of new oil to make new plastic, right?
That is the most controversial part of the whole equation. The study in the journal Science laid out 4 high-impact policies to achieve this.
Okay, what are they?
1 is mandating 40% post-consumer recycled plastic in all new products. 2 is a massive investment in waste collection and management, especially in lower income regions. But number 3 is the one that makes the industry shudder.
Which is?
Capping new, or virgin, plastic production at 2020 levels.
Capping production, full stop. I can just imagine the oil and gas executives' reaction to that. If the global demand for plastic is projected to keep rising as the developing world gets richer and buys more stuff, how can you cap production without causing massive shortages and price spikes?
You can't, unless...
Unless what?
Unless you get really, really good at recycling. If you cap the supply of new material, the only way to meet rising demand is to start mining the landfills. You're forced to use the trash you already have. It creates the economic pull for circularity.
It's like someone telling you, we're not delivering any new water to your house, so you'd better figure out how to filter and reuse what's already in your bathtub.
That is a terrifying but perfect analogy. It makes the point.
But this brings us to the big technological bottleneck. Because right now, filtering the water in the bathtub or recycling our existing plastic is kind of a lie, isn't it? I've read over and over that mechanical recycling is fundamentally failing us.
It's not a complete lie, but it has severe, and I mean severe, physical limitations. And that brings us right to the next big topic, the mechanical versus the molecular revolution. We really need to understand the basic physics here.
Okay, walk me through it. I put my plastic bottle in the recycling bin. The truck picks it up. What happens next in the traditional system?
Traditional mechanical recycling is, at its heart, very simple. You take the bottle, you wash it, you shred it into little flakes, and then you melt those flakes down and push them through a die to make pellets.
Sounds straightforward enough.
It is, but plastic is a polymer. And a polymer is a very, very long chain of molecules all linked together. You can think of it like a long strand of spaghetti. The length of that chain is what gives the plastic its strength and flexibility.
Okay, so long spaghetti is strong plastic.
Right. But every single time you melt it down, you're subjecting it to intense heat and shear forces. You are essentially chopping that spaghetti into smaller and smaller pieces. The polymer chains break.
So the quality degrades every time.
Significantly. It loses what chemists call its molecular weight. The plastic becomes more brittle, it turns yellow or gray. This is why you can't just turn a recycled water bottle back into another water bottle 10 times in a row.
So where does it go?
Usually you turn that bottle into something less demanding, like fibers for a carpet or plastic lumber for a park bench. This is what we call downcycling.
Once it's a park bench,
Yeah.
that's the end of the line, right?
That's the end of its useful life. The next stop is the landfill. So mechanical recycling, in many cases, is just a way to delay the inevitable. It buys us one extra life, but it doesn't close the loop.
Plus, you mentioned it can't handle contamination.
No, and this is a huge problem. You can't mechanically recycle, say, a plastic tray that held raw chicken back into a food-grade container. The risk of bacteria or chemical toxins surviving the relatively low melting temperature is just too high. The FDA and other regulators simply won't allow it.
So we hit a wall. And this is where the big 2026 breakthrough comes in, molecular recycling. I've also heard it called chemical recycling. Are they the same thing?
They're largely interchangeable terms. The core difference is that we are no longer just melting the plastic structure. We are fundamentally breaking its chemical bonds. We're going all the way back down to the molecular or even atomic level.
That sounds incredibly energy intensive.
It can be, yes. But the promise is something called circular naphtha. Naphtha is the basic petrochemical feedstock derived from oil that we use to make no plastics.
So with molecular recycling, you take that old park bench or that contaminated chicken tray.
And you break it all the way back down into its constituent gases and oils. Through processes like pyrolysis or gasification, you effectively turn it back into a liquid that is chemically indistinguishable from virgin naphtha.
So you're not just reheating the omelet, you're turning the omelet back into the eggs.
It's even better than that. It's
Yeah.
like turning the omelet back into the fundamental proteins and lipids that make up the egg. The output is what the industry calls virgin quality feedstock.
Okay, I have to push on that term, virgin quality. Is that real, or is that just clever marketing spin from the chemical industry? Can you really take a mix of dirty diapers and use motor oil bottles and turn that into a material that's safe enough to make a baby bottle?
Chemically, yes,
Right.
because the process is essentially a distillation. You're heating it to such high temperatures that you strip away all the contaminants, the dyes, the dirt, the food residue, the additives. You are left with the pure, basic hydrocarbon molecules. So from a legal and a chemical standpoint, it is identical to the stuff that comes out of an oil refinery.
Okay, that does sound like a silver bullet for the contamination and downcycling problems. But you mentioned the energy. If I have to heat this plastic waste to 1,000 degrees to break those bonds, aren't I just trading a plastic pollution problem for a massive climate change problem?
And that is the number one criticism of these technologies. Pyrolysis, which is essentially cooking the plastic in an oxygen-free environment, takes a huge amount of thermal energy. If you're powering that process with a coal-fired plant, you might be defeating the purpose.
Right.
But this is where the next chapter, the biological revolution, really enters the conversation. And this is where things get truly exciting.
The enzymes. This is the part of the research that honestly feels like science fiction. Plastic-eating bugs.
It does feel that way, but it's really just biology doing what it's always done. Enzymes are catalysts. They're complex proteins that organisms create to speed up chemical reactions. Your own body is using enzymes right this second to break down your lunch.
Okay, I get that.
So a few years ago, scientists started asking, has nature already figured this out? Can we find a microbe somewhere that has evolved to eat plastic?
And where do they look?
In the obvious places. Compost heaps, landfill sites, plastic recycling facilities, and they found them. They found bacteria that had evolved the ability to nibble on peat plastic, the stuff water bottles are made of.
Nibble. That doesn't sound very fast or industrial scale.
It wasn't. It was incredibly slow, but then they took that naturally occurring enzyme and brought it into the lab. They used a technique called directed evolution, where they intentionally mutated the enzyme's genetic code over and over again, selecting for the versions that worked faster and more efficiently. They basically put the enzyme through a super fast-forward evolution.
They supercharged it.
They turned it into a monster. The result is an engineered enzyme called PT221M, and the performance stats are just wild. It can break down 95% of bottle-grade peat powder back into its basic chemical building blocks, its monomers, in just 24 hours.
Wait, 24 hours? From a solid to a liquid?
In 24 hours. And here is the absolute key difference from those high-heat chemical recycling methods. This process happens at 60 to 70 degrees Celsius.
That's barely anything. That's the temperature of very hot tap water.
It's the temperature of a mild sauna. Compare that to the 400 to 700 degrees needed for pyrolysis. The energy savings are enormous. The overall greenhouse gas emissions are calculated to be about 43% lower than making virgin plastic from oil.
That completely changes the energy argument against advanced recycling.
It does, but the real superpower of this enzyme, the thing that makes it a true game changer, is its specificity. It's like a lock and a key.
Explain what you mean by that.
A high-heat process like pyrolysis is a blunt instrument. It's a hammer. It just smashes and boils everything. Enzymes are precise. They're like tiny biological scissors. An enzyme designed to break the bonds in peat plastic will only break those specific bonds. It will completely ignore everything else around it.
Why does that matter so much?
Think back to the textile problem we talked about. A poly-cotton blend t-shirt. 50% cotton, 50% polyester, which is a type of PET.
Right. Currently unrecyclable.
Yeah.
Landfill.
Exactly. It's trash. But
Yeah.
if you take that t-shirt and you put it into a vat with this engineered enzyme, the enzyme will literally eat the polyester, dissolving it back into its liquid monomers, which you can then use to make new virgin quality polyester.
And the cotton.
The enzyme leaves the cotton fibers completely untouched. It doesn't recognize them, so you just filter out the pristine cotton pulp, which you can then recycle mechanically into new cotton products. You save both materials from a single blended item.
That is incredible. It chemically unweaves the fabric.
It solves the blended fiber problem, which is arguably the single biggest headache in achieving circularity for the fashion industry. And this isn't just a lab experiment anymore. A company in France called Carbios is building their first industrial scale plant right now. It's designed to process 50,000 tons of this kind of waste per year. This technology is at TRL 9, Technology Readiness Level 9. It's ready for prime time.
Okay, this is amazing. So we have the new laws forcing the change, and we have this revolutionary technology to break down the material. But there's a crucial step in the middle that I feel like we always gloss over, the sorting.
The sorting bottleneck, yes.
You mentioned the red bottle versus the clear bottle earlier.
Right.
But let's take an even simpler case. I throw a bleach bottle and a milk jug into the same recycling bin. They're both made of the same plastic, HDPE. Can't we just melt them down together?
Absolutely not. And this is a critical point. The plastic in that bleach bottle can absorb some of the chemicals it held. It's called flavor and odor contamination. If you mix that plastic into a batch that's intended to make new milk jugs, you could be contaminating the food supply. You have to keep food grade and non-food grade streams completely separate.
But to a sorting machine, a white HDPE bottle is a white HDPE bottle. How can it possibly know what was inside it?
Right now, it generally can't. Most modern sorting facilities use near-infrared or NIR scanners. They bounce a beam of light off the plastic, and the reflection tells the machine what kind of polymer it is. Oh, that's HDPE. That one's PT. That one's polypropylene.
But it's blind to the history of the object.
It's blind to context. It can see the material, but it can't see what the material was used for. It doesn't know if it held milk or poison.
So what happens? Do we lose a huge amount of potentially valuable food-grade plastic because we have to play it safe and assume it's all contaminated?
That is exactly what happens. We have to downcycle huge amounts of high-quality plastic into lower-value applications just to be safe. To fix this, we need the package to be able to talk. We need it to tell us its own story.
This is where the digital watermarking comes in. Holy Grail 2.0.
Yes. The idea is to embed a digital passport directly into the packaging itself.
So is this like a QR code? Because I can't imagine product designers are going to be happy about putting a big, ugly QR code on their beautiful packaging.
No, that's the genius of it. It's essentially invisible to the human eye. You can think of it like a digital mosaic. It's a code about the size of a postage stamp that gets tiled thousands of times all over the surface of the plastic label or is even embossed directly into the mold of the plastic bottle itself.
So I can't see it, but a special camera can.
A high-resolution camera mounted over a conveyor belt that's moving at 3 meters per second can see it perfectly. And because the code is repeated all over the surface, it doesn't matter if the bottle is crushed or twisted or partially covered in grime, the camera is guaranteed to get a clean read on at least one of those thousands of tiny watermarks.
And what information is in that watermark? What does it say?
It contains a digital recycling passport. It tells the machine everything it needs to know. I am a milk jug, manufacturer, dairy quart resin type, food grade HDPE. This is a recyclable item. Recycle me with other food grade plastic.
And the machine then does what? Kicks it into the right bin.
Instantly. A precise jet of compressed air fires and knocks that milk jug into the food grade HDPE bin. A fraction of a second later, a bleach bottle comes by, the camera reads its passport, and it gets sorted into the non-food HDPE bin.
This would allow us to create pure streams of material.
It would allow us to create, for the first time at scale, a reliable stream of what's called food-grade recycled polypropylene, or RPP. Right now, RPP is basically a unicorn. It's incredibly valuable and incredibly rare because of this exact sorting problem. This tech could unlock that.
It's really amazing to think that the solution is basically just making our trash smart.
Yeah.
Giving it a voice.
In a circular economy, the data associated with the material is just as valuable as the material itself. If you lose the data, you lose the value.
Okay, I want to pivot now to something that feels completely different. So far, we've been talking about better ways to recycle the plastics we make from fossil fuels. But there's a whole other school of thought that says we should stop using oil entirely.
The bioplastic frontier.
And the source material focuses on algae.
Good old pond scum.
I have to admit, the idea of making a cup or a shirt out of pond scum, there's a certain yuck factor to it. Why algae? Why not corn? We already have PLA plastic made from corn in compostable cups.
Corn is what we call a first-generation feedstock, and it's problematic. To grow corn specifically to make plastic, you need huge amounts of arable land. You need fresh water. You need fertilizers, which have their own environmental footprint.
And you're competing with the food supply.
You're directly competing with the human and animal food supply chain. In a world with growing food insecurity, using farmland to grow plastic instead of food is an ethically complicated choice.
So algae is the ethical alternative. How is it better?
Algae is basically a weed. You can grow it in places you can't grow food. You can grow it in wastewater from cities. You can grow it in salty, brackish water on coastlines. You can grow it in closed-loop vertical farms in the middle of the desert. It doesn't compete with food crops for land or fresh water.
And it grows fast.
Incredibly fast. Some strains can double their biomass in just a few hours. And while it grows, it's a carbon vacuum. It just sucks CO2 out of the atmosphere. So the plastic you ultimately make from it is potentially carbon negative.
Okay, so how do you get from that green, slimy stuff to a hard, clear plastic cup?
There are a few different pathways. One is similar to corn, where you harvest the algae and fermented sugars to create PLA plastic. But the really cool one, the one that's getting a lot of research funding, is a type of bioplastic called PHA.
PHA. What does that stand for?
Polyhydroxyalkanoates.
Of course it does.
PHAs are fascinating because the algae basically makes the plastic for you inside its own cells.
What do you mean by that? It just grows plastic.
Pretty much. When an algae cell is stressed, when it has a lot of carbon to eat but not enough of other nutrients like nitrogen or phosphorus, it starts storing that excess energy. Humans store excess energy as fat in our bodies. Algae stores it as little granules of PHA polymer inside its cell walls.
So the plastic is basically algae fat.
That's a great way to think about it. It's a natural biological energy reserve that just happens to have the properties of a very useful plastic. We can harvest the algae, break open the cells, and extract these plastic granules.
That is wild. But hang on. If it's a natural energy storage material, does that mean that other things in nature know how to break it down?
Yes, and that is its #1 selling point. PHA is genuinely biodegradable, even in a marine environment. If a bottle made from PHA ends up in the ocean, the bacteria in the water look at it and say, hey, food. They already have the natural enzymes required to digest it. It breaks down completely in about 1.5 to 3.5 years.
Compared to 500 years for a standard PT bottle.
It's not even in the same ballpark.
Okay, I have to ask the obvious question then. If this stuff is carbon negative, grows in wastewater, and safely biodegrades in the ocean, why isn't everything on the planet made of PHA right now? Why are we still drilling for oil?
Two words: cost and scale. It always comes down to the money. Fossil fuel-based plastic is unbelievably cheap because the industry has had a century to optimize every single step of the process. Right now, algae-based plastic is about 3 to 5 times more expensive to produce.
That's a pretty steep premium for consumers to swallow.
It is. And there's also a big processing challenge. Algae is mostly water. To get the PHA out, you have to dry it all out first. That process, called dewatering, can take a huge amount of energy. And if you spend a ton of energy from the grid to dry the algae, you can quickly wipe out your whole carbon-negative benefit.
So how do we fix the math? How does it become competitive?
The solution is what's known as the biorefinery model. You stop thinking about growing algae just for plastic. You grow it to extract the highest value products first.
Like what?
Things like omega-3 fatty acids for nutritional supplements, or special pigments for natural food colorings or cosmetics, or high-quality proteins for animal feed. You extract and sell those for a very high price.
And the plastic?
The plastic is what you make from the waste biomass that's left over. It becomes a cheap byproduct instead of the primary product. You use every part of the algae.
The old use every part of the pig philosophy.
Exactly. And to make it even more efficient, scientists are now using genetic tools like CRISPR-Cas to edit the algae's genome. They're engineering new strains that are designed to produce more PHA and less of the other stuff, turning them into tiny, hyper-efficient biological factories.
It's a complete reimagining of where our materials come from, not extraction from the ground, but cultivation in a bioreactor.
That's the paradigm shift of the 21st century.
Now, I want to use that to shift to something much heavier. Literally, heavy industry. We've been talking mostly about packaging, which is lightweight and single-use. But the next chapter in our research takes us to wind turbines.
The hidden giant of the renewable energy waste stream.
I think for most people, you look at a field of wind turbines and you see a symbol of pure green energy. And it is for the 20 or 25 years that it's spinning. But what happens at the end of its life?
That's the dirty secret. A modern wind turbine blade is a monstrous piece of engineering. It can be 45, 50, sometimes over 100 meters long. And for the last 2 decades, they have all been made of thermoset composites, usually an epoxy resin reinforced with glass fiber.
And that word thermoset, that's the villain of this story.
It is. The best analogy for a thermoset plastic is a boiled egg. A raw egg is a liquid. You can separate the yolk from the white, but once you boil it, the heat causes the proteins to cross-link and form a solid, irreversible structure. You can never, ever turn a hard-boiled egg back into a raw egg.
So once a thermoset plastic is cured, it's locked in that shape forever.
It's chemically locked. You can't melt it down like you can a milk jug. If you heat it up, it doesn't melt. It just chars and burns. So when one of these massive blades reaches the end of its lifespan, you can't recycle it.
So what do they do?
They bury them. There were these infamous photos that went viral a few years ago of bulldozers burying hundreds of these giant white blades in a massive landfill in Wyoming. It was a PR nightmare for the wind industry.
It looks awful. We're literally burying the symbol of our green salvation in the ground.
It's a terrible look. So the industry has been racing to find a solution, and the answer is a shift to thermoplastics, specifically a new liquid thermoplastic resin called helium.
How is helium different from the old epoxy?
To stick with the analogy, it's not a boiled egg, it's more like a bar of chocolate. It's solid and hard at room temperature, but if you gently heat it up, or if you use a specific chemical solvent, it dissolves back into a liquid. The polymer chains don't cross-link.
So at the end of the blade's life, you can just dissolve the glue, basically.
You dissolve the resin. You can then recover that liquid resin to make new blades or other acrylic products, but just as importantly, you can recover the reinforcing fibers, the valuable glass or carbon fibers, completely intact and ready to be reused.
So this seems like a no-brainer. Why isn't every new wind turbine being made with this recyclable thermoplastic resin right now?
Well, this is where we run into a fascinating conflict between operational performance and life cycle sustainability. It's what the research calls the carbon fiber paradox.
Carbon fiber. Everyone loves carbon fiber. It's the material of supercars and fighter jets. It's super light and super strong.
It is. And for a wind turbine, lighter and stronger is better. A lighter blade is more efficient. It captures more energy from the wind. But the process of manufacturing carbon fiber is a climate nightmare.
Give me the numbers. How bad is it?
Okay. According to the Life Cycle Assessment Study, to produce 1 kilogram of glass fiber takes about 32.5 megajoules of energy.
Okay.
To produce 1 kilogram of carbon fiber takes 959 megajoules of energy.
Whoa, stop right there. Did you say 32 versus 959? That's almost 30 times more energy.
Yes. It's an incredibly energy-intensive process to bake those carbon strands at thousands of degrees. So here's the paradox. You can build a blade out of recyclable thermoplastic and super light carbon fiber. It will generate more electricity over its lifetime because it's so efficient. But you start its life with such a massive carbon debt from the energy it took to manufacture it that it might take years of spinning just to pay back the carbon emissions from its own creation.
So a technologically worse blade, one made of heavier glass fiber, might actually be the better choice for the planet overall.
The study concludes that for most onshore turbines, yes, the glass fiber thermoplastic blade is the current eco-winner. It has a 16 to 22% lower total carbon footprint across its entire life cycle. It's the less sexy engineering choice, but it's the right choice from a climate perspective.
That must be a really tough sell to engineers who are trained to always push for peak performance and efficiency.
It forces us to redefine what performance means. Is peak performance just maximizing kilowatt-hour output? Or is true performance measured by the net positive impact on the environment?
This is a perfect lead-in to our final chapter, the nuance. Because after hearing all of this, the failures of mechanical recycling, the complex regulations, the energy trade-offs, I feel like a lot of listeners might just throw up their hands and say, you know what, let's just ban plastic. Let's go back to glass bottles and paper bags. Life was simpler.
I hear that sentiment all the time. Let's just make things like they were in the 1950s. But the data, specifically from these comprehensive life cycle assessments, or LCAs, warns us that this would be a huge mistake.
Why? I mean, glass is infinitely recyclable. It's made from sand. It feels so much more natural and pure.
It is, but it is incredibly heavy. If you replace every plastic soda bottle in the country with a glass equivalent, you're tripling or even quadrupling the weight of every truckload of beverages being shipped. That means more diesel fuel burned, more wear and tear on roads, more transport emissions.
So you solve the plastic waste problem on the beach, but you make the climate change problem worse.
Dramatically worse. And that's before you even consider the manufacturing process. Melting sand into glass requires furnaces that run at 1,500 degrees Celsius. Melting plastic pellets takes about 200 to 300 degrees. The energy budget to make a glass bottle is enormous compared to plastic.
Okay, what about paper? Paper straws, paper bags at the grocery store. Everyone's switching to paper.
Paper has its own set of issues. It has a huge water footprint from growing the trees and processing the pulp. And very often, to make paper packaging useful for food, it has to be coated with a thin layer of plastic.
Right, to keep it from getting soggy.
Which then makes it a mixed material that's almost impossible to recycle. But the biggest, most important argument for plastic, and this is the one that always surprises people, is its role in preventing food waste.
Explain that connection for me.
Plastic packaging is an incredible barrier technology. It keeps oxygen out and moisture in. The classic example is a cucumber. A cucumber wrapped in that thin plastic shrink film will last for 14 days in the fridge. An unwrapped cucumber lasts maybe 3 days.
And if that cucumber rots and gets thrown out?
It goes to a landfill where it decomposes without oxygen and releases methane, which is a greenhouse gas that's 80 times more potent than CO2 in the short term. The carbon footprint of global food waste is larger than the emissions of most countries. If banning plastic packaging leads to even a 20% increase in food spoilage, we've absolutely shot ourselves in the foot, environmentally speaking.
We've fixed the visible litter problem on the street, but we've made the invisible climate problem much, much worse.
Exactly. As one of the reports puts it, we must be mindful not to fix a problem by removing one of the solutions.
So what's the synthesis here? After this entire conversation, what's the takeaway? We aren't breaking up with plastic.
We are fundamentally renegotiating the relationship. We can't ban it entirely. We need it for sterile medical equipment, for lightweight electric cars, for wind turbines, for food security. But we absolutely cannot continue to tolerate the waste.
So the goal isn't elimination. The goal is circularity.
The goal is to keep the carbon molecule in play, to treat plastic not as a disposable commodity, but as a valuable, durable material. Through the enzymes, through the digital watermarks, through the advanced chemical recycling, and through the smart regulations that make waste expensive, we want to keep the incredible utility of the material without the permanence of the pollution.
It's a hugely complex future, but it feels like for the first time, we actually have a coherent plan that addresses the chemistry, the economics, and the law all at the same time.
2026 is the year the plan goes live. It's going to be messy, it's going to be expensive, and it's going to be difficult. But the alternative, that business as usual scenario, is simply not an option anymore.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.